All right, so unfortunately, not all of our volumes are going to be flesh along their axis of revolution over the entire region that we are revolving. So if they are not solid all the way around the axis of revolution, then we are going to have to use what's called the washer method. So sometimes, again, this is just a result of the way that it's being revolved. Or maybe you actually have something that has a full like hole inside of it that you are moving around. So if you are taking g of x and the square root function here, so square root of x and 1, and revolving from 1 to 4 around the x-axis, notice that this is the little piece that you're revolving. So when we do that like reflection over here, in this piece, that's what's going around and around, okay? Almost like a little melon shape, if you will. I personally, when I do washer only, I'll sometimes draw like the inside, but I feel like sometimes if I draw the outside, I don't know, maybe it's okay. But I want to make sure that I can see that it's called a washer. So think about like a building washer or a plumbing washer. That's where this comes from. Where a disc is more like a quarter, this has a hole in it, like a washer. That's why it's called washer method, okay? And so like this is a good 3D image of what's going to be generated. It kind of looks like that bullet shape from a previous example, but with a hole in the middle, okay? So what do we need to do here? Well, we have two circles that we are finding volumes of. So let's go back up here really quickly. When you have that dx piece that you're looking at, if I were to try to figure out the outside volume, I would use this, what I'm going to call big R, to find that outside volume, right? So I'm going to do pi and then like big R squared dx to find that big volume of just that piece, and then go all the way down. Then I have this inside washer piece, that whole piece. Well, that is this radius. I'm going to call that little r. And you can notice, actually, in this example, it's the same everywhere, but that's not always the case. And then in order to find the total volume, if you were to find the volume of any shape, you would need to find the outside volume and then take out the inside volume. So these are two separate calculations. We don't put them in the squared on the inside, like we don't do this, f of x minus g of x, and then square it, okay? That's not something that we do. We keep those as two different radius squareds because I'm finding an outside volume and an inside volume. All right, example 1 here, find the volume of a solid of revolution if we have a graph of x and 1 over x, and I'm looking from 1 to 4 around the x-axis. So here is f of x equals x. Here is g of x equals x. They do intersect at 1. And then we go to 4. And I'm going to then be taking this piece around. Okay, so this is where I like to draw in my little reflection piece. Okay. And then I'm revolving around the x-axis. Okay, I'm going to go ahead and draw. There's my little radius. And there's my big radius, right? Okay, so big R, in this case, is going to be defined by my f of x function, right? Like if this was disk method, and I were to be taking this and finding this big piece around, I'm going to say that big R is f of x, which is x. Then I have my little function here. That height is always g of x as I go around and around and around. So little r equals g. Oh goodness, I did not All right, let's go ahead and get this all set up then. So I want to integrate from 1 to 4 pi times big R squared minus, big brackets here, little r squared. It is a little more work, but you could do like these as two separate volumes if you wanted to, and then they're going to simplify to this piece right here. All right, let's take the pi out. I'm going to have 1/3 x cubed minus the natural log. Oh, I lied to you. I did, and uh-oh. This ends up being x to the -2, right? So I'm going to have x to the -1 divided by -1, so plus 1 over x from x equals 1 to 4. All right, plug in 4, plug in 1, we subtract, and when you simplify, you do get 81/4 times pi. All right, let's look at another example. Find the volume. We're going around 4 minus x below and below the x-axis, bounded above by this function, below by the x-axis from 0 to 4. And then I'm going around something that's not the axes. So this is the first time we're going to be looking at something like this. This one has a little bit of a trick to it when you're trying to find your radii, okay? So let's graph f of x. So this is a line, slope of 1, y-intercept of 4. And I'm bounded below by the x-axis, so this is my region. And this does have a 0 at 4, so this is my region. So you might think like, oh, if I were to revolve this around the x-axis, I would make a cone, okay? But I don't want to revolve around the x-axis. I want to revolve around the line y equals -2. So let's go ahead and do that reflection. And so let's find big R. Big R goes from here all the way around, right? This is where when we draw the circles, it gets a little bit crazy, but that's okay. Okay, so big R. Well, this function is this height, 4 minus x. That's not going to get me my full radius. Like that piece is 4 minus x. This length is always 2. So this total length of r must be 4 minus x plus 2 or 6 minus x. Okay, my little r is the same no matter what. It's always 2. And one thing that gets confusing is you are in the negative axis, and so it's like, why are we adding? And so think about it in terms of length, okay? For radius, the big radius, like 4 minus x is always this piece, and then in order to get to your axis of revolution, you need to add 2 more. Okay, so here it's 2 because x equals 4, 4 minus 4, 0, plus 2, I need that to be 2. Over here, when I plug in x equals 0, I need that to be 2 plus 4. I need that to be 6. Okay, so you want to double check and make sure that you are doing this correctly. To save time on this one, we're just going to set it up. And I always like to do the work for big R and little r off to the side like this, so I can then just plug into our formula. So volume is going to be 0 to 4, excuse me, of pi big R squared minus little r squared dx. Now you would expand these, simplify. If you want to pause this and try that, I will tell you that the answer is 160 pi over 3. So you can double check your calculus there if you wanted to work on that.